Dear friends, welcome to this Electrical Engineering Knowledge Sharing channel, AMP Power System. We are on workshop 5. In this workshop, we have already completed one session where we have discussed about generator sizing for base load, for motor starting, as well as combined base load as well as motor starting. Today we are going to discuss session 2 of workshop 5. In this session we are going to discuss about the distribution transformer sizing for residential purpose. In this workshop 5 we have said that we will be putting all these various electrical equipment, power electrical equipment sizing calculation. Today we are going to discuss the transformer sizing for distribution purpose in residential area. Then we will be discussing about the distribution transformer for the power distribution in the industrial or in the plant. Then we will be discussing transformer sizing for the motor starting. Then we will be also discussing the distribution transformer sizing for combined motor starting as well as plant distribution power. And then we will discuss your short note on this grid transformer or the network transformer sizing. So let's discuss. We will try to limit our session within 30 to 40 minutes. So based on that we will proceed. So before going into discussion on this transformer sizing, let's see what are the various type of transformers which could be present in a power distribution network or power transmission network. So starting from the generating station, we will proceed up to the consumer end, and on the way we will see how many type of transformers are present, and we will discuss how we can do the sizing of those transformers. So let's start from the generating plant. We have already said this is a generating plant where the generators are located. From the generators, it may be 11 kV generators, or it may be 33 kV generators, or it may be 6.6 kV, or it can be 3.3 kV. There are various type of size voltage level is available. Once this sometimes this generation is directly used, but most of the cases when the your network is working, when the DNO, when a distribution network operator is using present, as well as power generation companies are present. So generally power generation company, they generate the power, then the step of the power at a high voltage, that could be 66 kV, or it could be 132 kV or 220 kV or 400 kV. This step of power goes to remote end. At the remote end there is a substation where they receive this power through the step down transformer, or they receive the power at the same 132 kV, then they put a separate distribution transformer. So there will be a step down transformer 132 kV, maybe it will be 11 kV. From there, suppose this is one of the way, suppose there will be another way, this is a suppose 132 kV switch yard at the remote end. So after receiving the power at 132 kV, then they go for the separate distribution transformer 132 kV by 11 kV, maybe one from this distribution company, or this is called DNO, it is a network operator. So this network operator, they can transfer the power 132 kV power, they can give to a consumer. So there is a consumer over here, he is receiving the power, or it could be instead of 33 kV, it could be 66 kV or 33 kV itself. This transmission voltage, it could happen like that. It may happen that at this end, again this DNO or this distribution network operator, he reduce the voltage 132 kV by 33 kV, and then this 33 kV voltage is going to the further switch gear, 33 kV switch gear. From here they are supplying power to the various. Suppose this power is going to one of the industry, this power is going to some residential purpose, this power is going to some local distribution for the area lighting, all these things, or area power distribution supply. So this could be industry, it is going to industry, this 33 kV feeder, this 33 kV feeder is going to maybe a huge residential complex, this 33 kV feeder is going to some area electrification. So these are different distribution may take place. So if this is going to a industry, so this 33 kV industry cannot use this power, so they have to transfer the power maybe 33 kV by 6.6 kV, and then 6.6 kV further distributed. This is going to some using housing complex, so they cannot use 33 kV, so they may transfer to 33 kV by 415 volt. So this may be another, it will go 33 kV by 415 volt. Sometimes they can convert is 132 kV into 33 kV, they can go 11 kV, then they will give 11 kV feeder. So it will be accordingly, it will be distributed. So now we are going to discuss first this area. So if you see here, there are two types of distribution transformer. There will be another distribution transformer maybe here, which is directly a step down. Suppose it is 11 kV, this switch gear is 11 kV by suppose 3.3 kV. And this 3.3 kV going to direct to motor. So this is one type of distribution, plant distribution transformer. This is for supplying power to the various loads. And this is another distribution transformer which is going to housing complex. This is another distribution transformer which is going to directly feeding the motor to dedicate the motor. And there may be another transformer which is going to motor as well as other loads. So this type of various distribution transformer could be present in the network. So we will now discuss in this portion first. So here we are discussing today this part. One of the feeder is going to a huge residential complex where they are supplying one feeder. Then the residential complex company, they are procuring this transformer. This is called a distribution transformer, that is 11 kV by 415 volt or 22 kV by 415 volt. This distribution transformer will be supplying power to the residential complex. So today we will discuss this part. Then we will go to discuss further this industrial distribution. Then we will go to this motor starting distribution. Then we will go to the combined. So this way 4 distribution type of transformer sizing we will do. After that we will go to this type of network transformer where this total power to be catered to the remote head. How we will size this? Then we will see the use note of this. This is called your generator transformer or step up transformer. This we will discuss. Okay. So today our discussion will be this distribution transformer for the residential purpose. This one. So if we see this distribution transformer from residential purpose, this distribution transformer when we are sizing, we have to start from the load of that distribution transformer. So our today's discussion, we are thinking in that way. We will limit this distribution transformer. We are thinking to supply power a housing complex. A housing complex, maybe there will be a 4 towers. 4 housing. There are 4 towers. What happens to this one? There are 4 towers. Each tower, it is a 22-storied building. Suppose 20-storied building, and each building has a 5 apartments. Each floor has a 5 apartments. So 20-storied building, 5 apartment means each tower has a 100 apartment. 100 apartment. And this type of 4 towers are there. So 4 into 100 means 400 apartments are there. And this 400 apartment, each apartment is 200 square feet apartment. Is 1,000, 2,000 square feet apartment, which is consisting 3 BHK apartment plus 1 guest house. Okay, 1 guest room. Like this, you can say 4 BHK, 1 small guest room. And this BHK is a standard 12 feet by 12 feet, means approximately 150 square feet. Then dining, similarly 120 by square, dining and drawing, living room maybe 400 square feet. This type of 400 to 2,000 square feet apartment, each apartment is 2,000 square. This type of one each apartment. This type of 400 apartments in these 4 towers. Okay, each tower has a 100 apartment. If we want to electrify this apartment, so we have to see what size of transformer either this company who is constructing this housing complex, they will provide, or the power supply company who is supplying power, who has agreed to supply power to this complex, what size of transformer he need to supply. Suppose entire power will be supplied at 415 volt. What about the upstream transformer? That may be 11 kV or 33 kV or 22 kV, but the utilization voltage will be 415 volt 3-phase 4 wire. So this type of apartment, if we want to supply without any interruption, then what will be the size of the transformer? So to start this transformer sizing, we have to start from each apartment. Now here when we will be sizing the transformer, there are 2 terminology we will be using very frequently. One is called demand factor, another is called diversity factor. What is demand factor? Demand factor we define when a particular house, in a particular house, maybe there are various loads are connected. Suppose there is the air conditioning load. Now you see, suppose there is you have a kitchen load, you have a heating load, you have a lighting load, yeah? Then you have a plug sockets, then you might have some other miscellaneous load you have. So this type of various loads are there. This is the total system of a house, total electrical system for a house. Out of these are each are one subsystem. Air conditioning is one subsystem, kitchen is one subsystem, heating is one subsystem, lighting is one subsystem, plug socket is one subsystem. These are the various subsystems. For each subsystem, we have to find out of this AC subsystem, whatever the total kilowatt connected to the system, or at a particular instant, what is the maximum number it can run or maximum kilowatt. When we want to decide this factor, we define it called demand factor. Demand factor is defined as this maximum demand of this subsystem or maximum running load on that subsystem, demand factor of a particular subsystem, demand factor. How we define this thing? This is equal to maximum running load or maximum demand on that particular subsystem, demand or running load, you can say maximum running load divided by total connected load. Total connected load. Suppose there are total 6 air condition whose total kilowatt is 10 kilowatt. Suppose. Now out of this 10 kilowatt, if I say the demand factor is 0.6, that means only at a particular instant of the 24 hours, maximum 6 kilowatt will be running. That means 0.6 total connected load 10 kilowatt. This is 10 kilowatt. So the 0.6 equal to 10 kilowatt. So how much the maximum demand? Maximum demand 10 into 6 means 6 kilowatt. That means though 10 kilowatt load is connected, but actually at a particular instant, this subsystem has a maximum demand of 10 kilowatt. In this way, each subsystem maximum demand we have to calculate. That is the first part. That is called demand factor. When all the demand is decided, demand factor, maximum demand we decided, now all this thing has a maximum demand. This has maximum demand, this has running, this has a running, some maximum demand, this has a maximum demand. Now all these maximum demand will not come simultaneously. There is a diversity in this. Suppose over a 24 hours, when the kitchen is running, air condition is not running, might be maybe one air condition is running and maybe half of the kitchen running. When the air condition is running, heating is not running, because heating and air conditioning are two opposite to each other. Or maybe only maximum when AC is not running, maybe winter time when the water geyser is running. So again the lighting load will not be, suppose night time when AC is running, lighting load will be very nice, will be running. Then there is a ventilation load, means all the fans are running. So these are among themselves, again there is a diversity. So actually although all these has a maximum demand, but all the maximum demand will not come simultaneously. To decide at a particular instant of a day how much total maximum demand can come, we want to find out that thing, we use a diversity factor. We call diversity factor. How we decide this thing? Diversity factor, we decide sum of the subsystem maximum demand. Sum of the, suppose there are 10 subsystems, so n equal to 1 to 10. Each demand has a maximum demand, suppose P maximum, P max, n. So these are each subsystem, how the maximum demand, will sum up all the maximum demand divided by maximum demand of the whole system at a particular instant, maximum demand of the whole system. So from here we can find the diversity factor. So if all the system has a maximum demand, we sum up all the maximum demand. So total maximum demand how much divided by at a particular instant how much non-coincident maximum demand can come on the system, we divide that thing. And this is obviously when you sum all these things, all together will be always more than the maximum demand. That means this factor is always greater than 1. Suppose if we say 60% of the all maximum demand is running at a particular instant, then what will happen? This will be 0.6. So that means this diversity factor will be, if it is a this divide 1 by, it will be, suppose whatever the amount this thing, suppose the maximum, this is about, if this is a 1 and this may be only 6.6, then equal to how much? 1 by 0.6. This is equal to 1.66. So that means when the diversity factor is 1.66, our maximum demand at a particular time is only 0.6 of the total connected. Okay. So in this way we can calculate this how much maximum demand of will be coming at a particular apartment. So these two factors we will be using in the calculation of the transformer sizing. So step by step I am going how we calculate the transformer sizing. When we will be going the transformer sizing, first we have to find out each apartment how much load we have, how much kilowatt or KVAR is there. That load we have to decide, connected load we have to decide. From the connected load we will calculate what will be the maximum demand of each subsystem. Once we decide the maximum demand of each subsystem, then from that we can connect by using the diversity factor how much maximum demand coming on a system for that particular apartment. Then the particular apartment will be another subsystem of the entire apartment. In this way, one house or one apartment, how is the maximum demand we will calculate. Then we will calculate the maximum demand of all the apartment. When all the apartment maximum demand is calculated, then we will calculate the using diversity factor this system which is supplying power the entire apartment, all the apartments, how much maximum demand coming on that. From that we can calculate the transformer sizing. So let us consider one typical, because all the apartment for simplicity of calculation we have considered all the apartments are 3 BHK similar same area, okay, and it is a we are calculating for the load which we are considering, this is for the 6 people living in a 3-bedroom apartment on that consideration. So in a particular apartment we will be using some table. So how we will calculate this thing, we have to tabulate the load first. So what the factor we will consider is a number one is your first point is your serial number, then the load description, then we'll use demand factor of each load, demand factor of each subsystem, then we'll calculate connected load, okay, connected load. Now here connected load we have a two part, one part is a kilowatt, another part is KVAR, because when we will be adding arithmetically we cannot do because this is a vector. So kilowatt is working this way, KVAR is working this way, VAR is working this way. So we have to, and KVA is this way. We will different direction depending on the power factor, depending on the angle. This is a KVA. So this KVA we cannot sum all together because it is different direction. So if we want to add all the KVA, what we have to do? We have to dissolve this easy kilowatt and KVA VAR separately. Then we will be adding all the kilowatt together because kilowatt will be this direction, VAR will be this direction, all kilowatt will be added, all KVAR will be VAR will be added, then we will calculate the total KVA of the system. We cannot simply calculate the KVA in this, only simply you calculate kilowatt to KVA, then you cannot add the all KVA to find the final sizing of the transformer, because transformer sizing to be decided in terms of KVA. We always decide transformer, we always mention transformer rating in KVA. So we have to find out each apartment how one KVA is there. So that KVA, each apartment we can find the KVA, then each apartment KVA, when you go for multiple, each has a different maybe different. So we cannot add all the KVA separately, or each subsystem has a KVA. Suppose AC has a KVA, ventilation has a KVA. These two KVA is not the same power factor, not the same direction. So we cannot sum up this together. So this all KVA to be dissolved into kilowatt and VAR, and then we have to add the kilowatt, we have to add the VAR, then we have to finally find out the resultant KVA. So what we have to do, we have to split this thing into two parts. One part is a kilowatt, another part KVAR. How we will do that? Using power factor. There will be power factor. This will be connected load. Then we will go using the demand factor, we will find out the maximum demand of each subsystem. Here also the same thing. How we will calculate maximum demand? Here will be kilowatt, here will be KVAR. And power factor will be remain same as per this initial one. So this table we will be using, and from the table we can calculate total maximum demand. Okay. So in this way we can find out number one load. Suppose your air conditioning load. If there is air conditioning load, so I have a we can write down air conditioning. One load is air conditioning. One load. Second load you have a suppose air conditioning kitchen load. Then third load is ventilation, means fan. Kitchen fan, bedroom fan, ventilation. Fourth load is your lighting load. Fifth load is your heating load. Sixth load is your plug sockets, where all the TV, then music system, all these things are connected. Plug socket. Vacuum cleaner to be connected intermittently. These are the mainly in a residential apartment, mainly this type 6 type of typical loads are there. So if you see it is a 3-bedroom apartment. So if you consider normally as per rule, 150 square feet room, you can cool down by 1 ton machine. 1 ton machine means about 1.5 kilowatt. 250 square feet house, you can cool by 1.5 ton, which is approximately 2 kilowatt. And more than 250, about 400 square feet, we need about 2-ton machine which is approximately 3 kilowatt. So if it is 100 square feet, you need about 0.8 which is about 1 kilowatt. So if we consider particular apartment, it is a 3 BHK apartment. How many 150 square feet which is need about 1.5 kilowatt into 3. 3 into 1.5 that equal to about 6 kilowatt. Then you need in this guest room is 100 square feet which is approximately 1 ton 0.8 ton machine which is approximately 1 kilowatt. So okay, 6 plus 1, and then you have a 3 plus 4, actually 4 number because 3 bedroom, and dining area also about 150. So there are total 4 room 1.56 kilowatt, and drawing room or living room, it is a big room, it is 400 square feet. So you need about 2 ton machine which is equal to 3 kilowatt. So if you calculate all this, it is approximately 10 kilowatt. And these are all single phase motor. So single phase motor power factor is very poor, nearly 0.8. So if we consider power factor 0.8, this is a 0.8 power factor. Air conditioning load, connected load is 10 kilowatt. Okay. Similarly, now the kitchen. In the kitchen, what you have? In the kitchen, approximately load in a standard good kitchen, it is approximately 10 kilowatt, because in the kitchen, what the equipment you have? You have a fridge, one normal fridge, then maybe one deep fridge or another small fridge will be there. Then you have a electric grill, then you have electric oven, they have a microwave, then you have a kettle. So if you consider kettle 2 kilowatt, okay, kettle about 1.5 kilowatt, you have your steam iron also in the kitchen area, that will be about 2 kilowatt. Then you have a electric grill about 2 kilowatt. Then you have a microwave which is about 1.5 kilowatt. Then you have a fridge and all this thing, it is approximately 300 watt, 0.3 kilowatt. So 4. Then you have a fridge, then microwave, steam iron, kettle, electric oven, microwave, then grill, electric grill you have, which is approximately 2 kilowatt. So if you consider all this thing, 2 to 4 to 6, 3, 9, about 10 kilowatt kitchen load. So we can consider kitchen load is approximately 10 kilowatt. And all this thing is mainly all are heaters. So the power factor is very good. So 10 kilowatt power factor, we can say 0.9 for this. Okay. So this is a 10 kilowatt. Then your ventilation means is all are fan. So we have a total how many? 3 bedroom, 4 bedroom, 4 fans, plus you have a dining area, drawing area, total maybe 8 fan 60 kilowatt, 8 fan 6 about 500 watt. You can say this is a 0.5 kilowatt. These fans are a small fan, so it is a power factor 0.8. Okay. Now lighting load is how much? It is approximately the total area. If you say all LED light, so 20 watt light is one room is enough. So it could be about 150 to 250 watt. 0.25 kilowatt is the lighting load. Then heating load, how much? Heating load, you have a 2 toilet, 3 toilet. 3 toilet about 6 kilowatt is the geyser, plus one maybe 6 to 7 kilowatt heater load. 6 kilowatt you can say, 6 kilowatt. Plug socket, maybe you have a total various area, maybe 20 plug sockets are there. So 20 plug socket is considered about 250 watt each plug socket maximum. So 20 into 250 means about 3 kilowatt, right? 3 kilowatt is a plug socket load. These are the total connected load of a house. How much it will be? It will be 10, 10, 20, 29, about 30 kilowatt you can say your connected load. Okay. Now this is the kilowatt. Now if you go to KVAR, how much KVAR equivalent will be there? So from there you can calculate the KVAR. I have done one small calculation, that is simply kilowatt, from the kilowatt divided by point power factor you get KVA. KVA equals to how much? 10 divided by 0.8. So this way you get the KVA. Once you get the KVA, and 0.8 power factor means sin phi, how much? Sin phi 0.8, 0.6 sin phi. So 1 KVA into sin phi, that equal to give your KVAR. So easily you can calculate all the KVAR. From the kilowatt divided by power factor, you will get the KVA. KVA into sin phi. Now cos phi is 0.8. Power factor means cos phi. Sin phi, how much calculate? Sin phi equal to 1 minus cos square phi. That under root. So you calculate 0.8 power factor means 64. 1 minus 64 and 0.36. If you square it, it is 0.6. So in this way, all this power factor can be calculated. And KVAR, I have already done this calculation on a small to save the timing. So if you see the KVAR, for this KVAR, for 10 kilowatt air conditioning load, the KVAR will be 7.5. Okay, 7.5. If you go to this ventilation, for this kitchen 10 kilowatt with a 0.9 power factor, this will be KVAR will be equal to your 4.78. Okay, KVAR this is a 4.78 kVAR. So if you go to the ventilation is equal to 0.38 kilowatt. Then your lighting load is a 0.5. We have considered lighting load here. Sorry, here maybe some other load will be there. So it will be 0.5 lighting load. For this lighting load 0.95 is the power factor. So it will be lighting 0.16. Lighting load power factor is a 0.95. Okay. Then you have a heating load. Heating load is a 6 kilowatt. It is a no KVAR because heating load all are heater. So it is unity power factor. Plug socket 3 kilowatt. So 3 kilowatt plug socket. If you take plug socket, it is approximately KVAR will be power factor. I am considering power factor 0.85 because it will be mixer multiple type of load. So it will be about 1.84 kilowatt. Okay. This will be the total kilowatt KVAR. Okay, for the connected KVAR. Now for this, if we consider the diverse demand factor for all this load, now how we will calculate the demand factor? We can write down here the separate column the demand factor for each type of load. Demand factor. Now if you consider the demand factor for each separately, because each has a different way it will be using, so demand factor for each is separate. Now if you consider this air conditioning if you see, now out of this air conditioning, nearly not more than 50% air conditioning will be running at one time, right? So this total connected load, whatever there, if we consider 60% is the demand factor, then it is we are in the same. So the demand factor for air conditioning system we are considering 0.6. Now the kitchen load, we will not be using 50% of the load at one time. Suppose when you will be doing the grill at that time you are not using oven, you are not using maybe microwave, you are not using the kettle. When using the kettle at the morning for heating water, at that time maybe grill is not used. So if you see in this way, this kitchen load demand factor will never be more than 0.4. Now ventilation system, out of this total 8 fan at a one time, not more than 50% fan will be running. So if we consider ventilation system 0.5. And lighting system similarly, how much lighting system will be also like this 50% maximum. Now heating load, it is a very poor because when only winter time the heater will be used, when the air condition is not there. Again, all the heaters you will not be using. Suppose a maximum at a time one heater will be running at one time. If that is the case, then the heating load, if we consider maximum demand factor 0.2, that is we are on the safe side. Then your plug socket similarly, out of this 20 plug socket, at a one time how many plug socket? Maximum 4 plug socket will be running. So it will be 0.2. So if we consider this is the demand factor for the system, secondly, this demand factor, there is a IEC where you can get this demand factor also. From 0.2 to 0.6, 0.7 demand factor is there, depending on if there is only one load. Suppose one air conditioning is running, in that case either air conditioning is running or not running, in that case demand factor will be 1. But as the number increases, demand factor gradually reduces. Okay, so if this is the demand factor, then for each subsystem we can calculate maximum demand how much. Now for this air conditioning system, if we apply 0.6, then what will be the maximum demand? This will be 6 kilowatt maximum demand because 0.6. This will be 4 kilowatt. Now 0.5 it will be 0.25 kilowatt. Then this will be also this is the maximum demand 2.5. Then 6 kilowatt, if you consider 0.2, then it will be 6 to 12 1.2 kilowatt. And then 3 kilowatt, how much? Heating load, you can say it is maximum 2 kilowatt because one heater may be maximum 2 kilowatt. So better to consider 2 kilowatt. Okay, 2 kilowatt means it is about you can say 40% demand factor. Then 3 kilowatt. Now this plug socket 3 kilowatt is 1. If you consider this 3 kilowatt plug socket at 0.2, it is a 0.85 power factor. So it will be approximately 0.6. So this will be the total kilowatt. Then corresponding KVAR how much? The KVAR, if you calculate KVAR, it will be 3.75 KVAR. This will be 1.91 KVAR. Okay, kitchen load is 1.95. Then ventilation will be equal to your ventilation equal to 0.19. Okay, ventilation 0.19, lighting 0.15, and then heating no KVAR, and then your plug socket will be your 0.6. Okay, plug socket will be 0.6 KVAR. So if you sum all this KVAR, it is coming now. This is a kilowatt. Now if you come this connected KVAR, how much connected KVAR? It will come approximately, if you calculate all this, so 7.5. So this is equal to total KVAR is coming 14.6 KVAR. Okay, So this is a connected 14.6. Now considering the maximum here, this maximum demand, how much it is coming? If you calculate all this maximum demand, it is coming about, total maximum demand is coming on this particular apartment, 6-person apartment, it is coming here, this coming 12.1, so you can say 12 kilowatt, okay? It is coming 6, 10, 10, 12, 6 and 4, 10, 10 to 12, 12, 12, about 12.8, about 13 kilowatt coming. And this KVAR is coming about 6.36 kilowatt, okay? This KVAR is coming 6.36 KVAR. So this is actually coming on maximum demand. So this will be our summary here. That means summary will be, we can consider our one apartment, okay? One apartment is total load how much? One apartment, 6 person is living, 3 BHK, okay, plus one guest room, 2000 square feet. So in that case, maximum connected load is 30 kilowatt, 14.6 KVAR, okay, and running load or maximum demand at a particular time is about 12 to 13 kilowatt, and KVAR is a kilowatt, KVAR is a 6.36 KVAR. This kilowatt which I got, 12.13 kilowatt running, summing all the individual load, okay. Now all the individual, what are the individual system? We have AC system, heating system, ventilation system, lighting system, all this subsystem. Each has a maximum demand. On summing all the maximum demand, we have got 12 to 13 kilowatt. So now we have considered sum of all the maximum demand is a, suppose 12 kilowatt or 13 kilowatt is the maximum demand. 13 kilowatt is the maximum demand. And at a particular time, how much maximum demand, that we want to know. This is equal to how much diversity factor. For this type of apartment, diversity factor is generally 0.6. So if we calculate this thing from there, we can calculate in this apartment at a particular time, how much maximum demand will be coming. Demand maximum for this particular apartment equal to how much? This equal to, demand will come over here. That means sum of individual demand, that is equal to how much? Sum of individual demand is 13 kilowatt. This is we got divided by into 0.6, right? Diversity factor, this is a diversity factor, this is equal to 1.66. 0.6 means 1.66, this divided by 1.66, that is the maximum demand. So if you calculate 13 divided 1.66, it will come approximately, how much? It will come is approximately 7 kilowatt, okay? If you calculate this 13 divided 1.66, 13 divided 1.66, this will come approximately 7 kilowatt, okay? This will give you 7, it is about a 12 kilowatt, 12 to 13, 12.7 kilowatt. This is coming of a particular apartment maximum demand at a time. And how much KVAR will be coming, we can also calculate the KVAR in the same way. So maximum demand for a particular apartment, demand maximum 7 kilowatt, and KVAR how much? KVAR will be similar to 6.36, 6.36 divided 1.66, 1.67, you can say 6.36 divided 1.67. So this is coming actually 3.8 and 3.8 KVAR. This is a particular apartment is designed for this. So corresponding KVA how much? KVA equals to a square of 49 plus 3.8 a square. If you calculate this thing, you will get 3.8 a square plus 49 a root equal to coming 7 point is about 8 KVA. This is a total maximum demand coming on the one apartment. We can calculate this is coming this way. So this is about the one apartment. Now we have to calculate now for the total system how much. This is for one apartment. This is your 30 kilowatt connected. Individual maximum demand sum is coming this. Maximum demand at a time using diversity factor, here we are using diversity factor 1.67, and this connected load, this is figure we got using demand factor of 0.6, okay. So with using the diversity factor 1.66 of this total summation of connected load, we got the maximum demand, kilowatt demand equal to how much? Kilowatt demand equal to 7 kilowatt, and the KVAR demand equal to 3.8, and KVA requirement is 8 KVA, okay. And how much the load demand power factor of the one apartment? Power factor equal to your kilowatt by kVA, kilowatt by kVA, right? So kilowatt equal to 7, kVA equal to 8. So equal to we are getting over here. Now we have to see entire apartment. Now we have how many apartment we have? We have a total 400 apartment. We have said already. Out of this 400 apartment, you see all the apartment are not occupied by the 6 people. Some of the apartment may be occupied only husband, wife and 2 children. Some of the apartment only husband and wife is living. Some of the apartment maybe senior citizens are living. Maybe son, daughter, they are not living there. So 6 people occupied the apartment where these parents, husband, wife and grandparents, grandchildren and husband, wife all are living. In this type of apartment, will how much? It will maximum not more than 25 to 30%. So if you consider most of the apartment will be occupied by husband, wife and the children. So maximum 2 children. In that case, if we consider this total 400 apartment, we can say 6 people living in this apartment. How much? It may be 150. And then 4 people living this type of apartment may be 200. And 52 people living this type of apartment may be 50. This is very optimum sizing, because some of the apartment will remain empty, nobody will be occupying. That we are not considering because we want to be very conservative in the calculation. So if we consider this way, that means this power requirement 7 kilowatt and 3.8 kVAR for one apartment, that is also it will be changing proportional to the number of person. So if this is required 7 kilowatt and 3.8 kVAR, it is proportional to people, how many people are living. So if you now go to the 4 people passenger, 4 people, so this is actually 4 people, then how much it will be? It will be proportionally, it will be changed. So if you go to 4 people, these will be coming approximately 4.8 kilowatt. 4.8 kilowatt, because it is simple formula. So it is calculating for 7 people, 6 people 7 kilowatt. If divided 7 divided by 6, that into multiplied by 4, it is coming about 4.8. And this corresponding, if you see the KVAR, we can also calculate the KVAR will be how much? It is for one apartment, 2 people, how many? It will be 50. It is approximately 2.4. 2.4 will be for this 2 people. So this will be the kilowatt requirement. Corresponding KVAR requirement, we can calculate how much? This will be approximately 7 is taking 3.8 KVAR. Now if you go to this next one for 4 people, it will be approximately 2.54. For 2 people, how much it will be? It will be approximately 1.27. This will be the requirement for the each house, each apartment, this type of apartment. So if we use this calculation this way, then now we can come back to the different, how much total kilowatt required, how much total each type of apartment, how much total kilowatt, how much total kVAR. So now if we go to that calculation, now out of this 400 people, so 150 apartment, so out of 400 apartment, 150 apartment requires at the rate of this. So kilowatt how much? It is kilowatt, we can put kVAR over here. So first group of apartment, that is 6 people apartment, 1 by 6 people apartment, how much it will be? It will be 150 into 7 kilowatt, right? Then 1 by 4 apartment, this second group apartment, how much? It will be 200 into 4.8, right? And it is a 1 by 2 type apartment, 2 people in one apartment. This is a 50 into how much? 2.4. This will be the kilowatt. If we sum all this thing, we'll get the total kilowatt how much? Okay. And similarly, kVAR how much? kVAR is equal to 150 into 3.8 for one apartment. Then this type of apartment how much? It is a 200 into 2.54. And third group apartment how much? 1.50 into 1.27. Yeah. So this will be the total. If you sum all these things, all this together, then you will get total kilowatt coming 2160, total connected kilowatt. And if you sum this to these will be coming 508 kVAR. This will be coming your 548. This is 548, 508 kVAR, and this is coming your 63.6 kVAR. 63.6. So if you sum this together, this is coming here approximately 63.6. It is coming total your 1120 5510 1120 kVAR. So this is coming 1120 kVAR. Okay. This is total coming, total maximum demand. Total maximum, sum of total maximum demand, yeah. So these three apartment, now this 150 group apartment is taking this is taking this is taking this. And 157 group 1050 kilowatt, this is 1960 kilowatt, this is 120 kilowatt. Now, question is, all these apartment what we are considering, all these, it is based on them is apartment maximum demand. So this group apartment maximum demand is this amount, this group maximum demand is this amount, this group apartment maximum demand is this amount. But all these maximum demand will not come at one time. It will be spread over the 24 hours at different time. Okay. So if you consider that is, so there is a diversity factor amongst the apartment. Out of this 400 apartment, there is another diversity factor. So, or each type of apartment there is a diversity factor. If we consider the diversity factor amongst all this thing is 1.67, so that equal to how much? Sum of all these loads. So kilowatt is how much? 2.2160. That divided by, at a particular instant, all this apartment is supplied by a transformer. This is a transformer which is supplying all this here. So how much total load coming on the maximum demand coming on the system? That is a, all this, considering all this subsystem sum is 2160. And if we consider diversity factor 1.60, so how much total coming on the system here? That is equal to, if we say P total, so PT equal to how much? That equal to 2160 divided by 1.67. That will give you approximately, if you consider this will give you, this will come about your 1.3 megawatt. This equal to 1300. That will be coming this kilowatt. If you calculate this, okay. Similarly, this is a power. Now, similarly, QT, total KVAR, how much it will come? Same way. Total KVAR, how much? 1120. 1120 divided by 1.6 diversity factor. So, this will give you a KVAR equal to 670 KVAR. So, this is the required. So, kilowatt wise, I need 1300 kilowatt. KVAR equal to total system. If we consider diversity factor 1.67, then we need 1300 kilowatt is the total active power, and 670 kVAR is your reactive power. Okay. Now from this we can calculate now what will be the size of the transformer. Now transformer, now we can go back to now how the system has worked out. System has worked out. This is our input transformer. From here it is going to a distribution board. It is suppose 22 kV by 415 volt transformer. Okay. Now from here we have a various circuits is going to various, suppose this circuit is going to tower 1. Okay. This is going to tower 2, this is going to tower 3, this is going to tower 4, okay, and then maybe one sphere is there, okay. Now from here, again, I will consider that part separately. Now from tower 1 is going to another, there will be another distribution board over here. From here maybe different feeder going for each floor, okay. Each floor has a 1 feeder. This is one going to floor 1, floor 2, floor 3, floor 4, like that. From here, floor 1 has how many? There are 6 apartments, right? 5 apartments. We have considered 20-story building, 5 apartments on each floor. So 5 apartments each floor means 100 buildings. So from here again there are 5 distribution board which is giving 5 circuit. So from here how it is going? It is going 1 feeder. It is going to a particular floor. Then this floor has a 5 circuit, 3-phase circuit, okay, or 6 circuit, 2 circuit on each phase, 1 sphere. Because 1 sphere is required for the lighting and all other crane, all the lift and all this thing, 1 feeder is required. So these way 6 feeders are there. This is going to each apartment. So this way if we come up to this, we have come over here. What is the maximum demand required at this point? That is, we have got maximum demand kilowatt required is 21. This is a maximum kilowatt is a 1300 kilowatt, and maximum KVAR at this point we need 1300 kilowatt and 670 kVAR to cater the entire load. So based on this, now we can, so this same amount power to be catered for this transformer. So for this residential purpose only, so how much kilowatt will be required? That kilowatt KVA or the, how much KVA will be required? That we can calculate from here. Now the KVA requirement for this total residential part only, for the apartment supply only, how much? That KVA, we know KVA equal to a square root of kilowatt plus KVAR square. This is equal to how much? 1300 kilowatt means 1.3 megawatt. That is square plus 7, how much we got? 670, right? We have got the KVAR equal to how much? KVAR we got 670. So 0.67, that is square. The root, if you calculate this thing, it will be coming to your 1460. Okay, this will come in 1460 kVA. This is coming, that means suppose it is 1.46 MVA, so it is equal to 1460 kVA. This is required for this residential part only. Now, in addition to this, what we have some other loads also. In this each apartment, each tower, there will be 2 crane, lift will be there. Then all the 20 story corridor and common area will be lighting, that will be there. So if you consider each crane is there, then there will be one pump, water pump will be there. So 35 kilowatt other load, 35 kilowatt if you consider 0.85 power factor. So 35 kilowatt, 35 divided 0.85. So this is equal to 41.76. So in 20 we can approximately summing it this actual what that kilowatt will be sum with this kilowatt. But for simplicity, we can calculate another 40 kVA is adding for the miscellaneous load for the various towers. That is a common load which is not part of the individual apartment. So it is coming total how much? 1500 kVA. That is the requirement of the transformer for this apartment. Okay, for this 4 complex. Now normally we do not consider the apartment this size. We put some margin because today you are putting this transformer. Then transformer we never allow to run on the same full rating. Generally we allow 80 to 90% rating, and we keep some option if some other loads coming in future, maybe some other contractor will be coming to work over there, they need some power, somebody maybe some work will be there, some your welding work, some braking work, all this thing require power supply. So generally considering this transformer will be running on 80%, not more than 80%, with some SPR capacity for the other purpose, we generally put 20% margin. So if we consider 20% margin, that means 1500 into 1.2, that will be size of our transformer size. This is equal to how much? 1800 kVA. So we can consider 1800 to 2 MVA, 2000 kVA transformer will fit for this purpose. So for this type of residential complex, we need about 1800 kVA transformer to meet all these 400 apartment as well as all the miscellaneous load, everything. That will be the size of the transformer. Now, on another point we have to keep in mind when we tell this transformer sizing, we have to clearly mention that this, if it is a oil field transformer, such as this 1500 kVA or 2000 kVA transformer, it will be oil field transformer. The transformer temperature, this loading will be such that transformer oil temperature, winding temperature rise shall not be increased more than the rated condition. Normally oil field transformer we allow while temperature rise is 100 degrees, not rise, total temperature 100 degrees centigrade, winding temperature 105 degrees centigrade, and the hot spot temperature of the winding is 115 degrees centigrade. While temperature 100 degree, 50 degrees centigrade ambient, 50 degrees centigrade rise, winding temperature 50 degrees centigrade ambient, 55 degrees centigrade rise, and hot spot temperature we allow another 10 degree, 50 degrees centigrade, 65 degrees centigrade rise. So this will be the guideline for the transformer. And this transformer we are not planning any overloading, and transformer as a 20% margin we have kept for the future use or any unseen requirement in the future. So this will be actual transformer requirement is for the residential part only 1300 kilowatt, reactive power requirement 670 kVAR, reactive power requirement. In addition to this, we have about 35 kilowatt power is required for the running the lift and the miscellaneous pumps and area lighting. So this total will be your transformer size. So if the incoming power supply 11 kV or 22 kV, it will be 22 kV by 415 volt. And this transformer tapping we can decide based on the no volt tap. If we in the system voltage 415 volt, then we have to mention this no load voltage will be 437 glass, because transformer has a 5% impedance, 5% voltage drop. If you want to include, then it will be 437. So this way we can find out the transformer sizing. So in a brief, we can say how we can do the transformer sizing for the residential purpose. First, each apartment or each house, how much connected load from the using demand factor, we have to calculate each subsystem, how much maximum demand. So each subsystem maximum demand or running load, how much decided, then summing all the subsystem and using diversity factor, we can calculate for a particular house or particular apartment, how much maximum demand is coming. So in a particular locality or any housing complex, such type of how many apartments are there, all the apartment, if it is a different type of apartment, then the power requirement is different, but each apartment we can calculate the maximum demand this way, total maximum demand. Then summing all the maximum demand of all apartment, we get the total sum of maximum demand. Using diversity factor, we can calculate the total maximum load, how much coming on the system. That should be catered by the transformer. In addition to this, we put 20% margin